Assalamu alaikum, everyone. Today's lesson focuses on finding the translational speed of a spherical boulder starting from rest at the top of a hill when it reaches the bottom of the hill. The top half of the hill is rough enough to cause the boulder to roll without slipping, but the lower half is covered with ice. So the boulder simply slides until it reaches the bottom of the hill. So stick around, join me till the end of this video, watch and learn. The question reads, solid uniform spherical boulder starts from rest and rolls down a 50.0 meter high hill as shown in the figure below. The top half of the hill is rough enough to cause the boulder to roll without slipping, but the lower half is covered with ice and there is no friction. The question is, what is the translational speed of the boulder when it reaches the bottom of the hill? Neglect rolling friction and assume the system's total mechanical energy is conserved. In this problem, we are not given the angle of inclination or how steep the hill is, so we cannot directly apply the usual kinematics equations. Instead, we're going to apply the law of mechanical energy conservation as implied in the question. Hence, we specify that at the top of the hill, point 1, 50.0 meters above the ground level being considered as our reference point. All right? The boulder only has potential energy without kinetic energy since it starts from rest. Its total mechanical energy, denoted by capital E sub 1, is equal to 50.0 capital mg, where capital M is the mass of the boulder and letter G is acceleration due to gravity. Right? 50.0 meter is the displacement, right? The initial displacement of the boulder with respect to the bottom of the hill, which we use as our reference level. When the boulder starts to roll without slipping down the rough portion of the hill, there is a friction force that must be acting on it, right? And the direction of this uh, friction force is always such as to prevent slipping or sliding. Take note also that the boulder is assumed to be a perfectly rigid and uniform sphere on a perfectly rigid surface. Moreover, a rigid sphere, such as the boulder, rolls without slipping because the normal force produces no torque. about the center of the sphere. Right. Now, when it reaches uh, point 2, right, which is a vertical displacement of 25.0 meters from the ground level, the potential energy has decreased to half its initial value. That is, at level 2, the potential energy denoted by capital P of E sub 2 is just 25.0 mg, right? The 50% potential energy that it lost is in fact converted to kinetic energy, all right? Both translational and rotational kinetic energy, all right? So aside from the linear uh, kinetic energy, there is also a rotational kinetic energy that is gained by the boulder, the fact that it is rolling or rotating about its axis, which happens to be the center, geometric center of the boulder, right? So, in other words, while rolling without slipping from point 1 to point 2, the boulder is losing potential energy, right? But at the same time, it is gaining an equal amount of kinetic energy, right? So that is how we figure out the transformation of mechanical energy from its original potential energy, all right, to uh, kinetic energy, both translational and rotational, as well as a decrease in potential energy, right? No amount of its original mechanical energy is being transformed to other forms of energy, such as heat, all right? It is specified in the problem that uh, the total mechanical energy of the boulder from start or from point 1 till it reaches the foot of the hill, all right, its total mechanical energy is conserved. All right, so as it continues to slide from point 2 to point 3, right, um, there is no more force of friction acting on the boulder. All right. This is because the lower half of the hill is covered with ice. All right. So when the surface is covered with ice, of course, we know that uh, there is no friction. But the boulder is still losing potential energy and gaining translational kinetic energy only. All right. Only translational kinetic energy is being gained as it slides down, all right, from level 2 to level 3, all right. There is no more rolling. So, in other words, there is no more what we call rotational kinetic energy that is being converted, all right. So, it is purely translational kinetic energy. So, when it reaches point 3 or level 3, all right, we say that all its uh, mechanical energy is already in the form of translational kinetic energy. So we label that here as E sub 3, all right, is simply the translational kinetic energy of the boulder. And it is based on this fact that we will be able to determine, all right, the instantaneous translational speed of the boulder, okay, when it reaches the foot of the hill. So we label that as B sub 3, which is our main target variable in this problem. Right, so continuing with our solution, we reiterate that when the boulder started rolling from level 1 to level 2, it is, in fact, losing potential energy, but at the same time gaining kinetic energy uh, in the form of translational and rotational. All right? So we have that equation here. And of course, we can express the translational kinetic energy of the boulder as 1 half the product of its mass, capital M, and the square of its speed, v sub 2, where v sub 2 refers to the instantaneous translational or linear speed of the boulder, in fact, of the center of mass of the boulder, all right, at level 2. And of course, the rotational kinetic energy also can be expressed as 1 half multiplied by the moment of inertia of the boulder, capital I, and the square of its angular speed, omega. Of course, the remaining potential energy, okay, we call it PE sub 2, all right, which now amounts only to 25.0 times capital mg. All right, this is the potential energy of the boulder when it reaches level 2. So, translating the meaning of the law of conservation of mechanical energy, we can have this equation. All right, the total mechanical energy of the boulder, which is simply equal to its potential energy when it started at level 1, which is, of course, 50.0 times capital Mg. All right? And we equate that to the sum of the kinetic energies, 1 half capital M B sub 2 squared, and 1 half capital I omega squared, and the potential energy of the boulder when it is at level 2, which amounts to 25.0 capital Mg. And simplifying this by transposing 25.0 capital Mg to the left side of the equation, or subtracting 50.0 capital Mg minus 25.0 capital Mg, all right, we come up with this simplified equation. 25.0 Mg, all right, this is uh, the amount of the potential energy of the boulder, all right, exactly at level 2 or point 2. And that is simply equal to the sum of the two kinetic energies, or 1 half capital M B sub 2 squared plus 1 half capital I omega squared. All right. So the simplified equation that we have earlier is now rewritten here, but this time we already express the rotational kinetic energy of the boulder, all right, uh, by using the formula for the moment of inertia of a solid sphere, because we are assuming that the boulder has a shape of a solid sphere, uniform solid sphere, whose moment of inertia is equal to 2 pips, all right, multiplied by its mass, capital M, and the square of its radius, all right, uh, with the axis of rotation being at the geometric center, that is. And then the angular speed omega squared is also substituted here by b sub 2 squared over capital R squared. All right. So for a body that is rolling without slipping, the kinematics equation that relates linear speed and angular speed, all right, where omega is equal to v, or the linear speed v, divided by the radius big R. Right? So we can simplify this equation and come up with this one, right? So we just cancel the mass, capital M, and also the R squared, or the square of the radius, capital R. So what does this mean? All right? This means that uh, regardless of the mass of the boulder, all right, or in other words, it doesn't really matter what the mass of the boulder is. All right? So in the question, the mass of the boulder was deliberately not given, right? Instead, uh, it gets canceled, okay, in the process of our computation, just like what we have here now, right? So what get now is a more simplified equation, that is 25.0 times acceleration due to gravity g, okay, is equal to 1/2 the square of the speed b sub 2 plus 1/5, all right, times the square of b sub 2, all right. We get 1 pip because 1/2 multiplied by 2 pips, of course, is 1/5. Or when we change 1/2 and 1 pip, or their sum, into decimal, that actually becomes 0.7. So 25.0 multiplied by acceleration due to gravity g is just equal to 0.7 times the square of b sub 2. Right. We can therefore isolate b sub 2 and come up with this working formula. So v sub 2, or the translational speed of the boulder when it reaches exactly at level 2, right? Simply equal to the square root of 25.0 multiplied by acceleration due to gravity g divided by 0.7. So when you do our math, or with the help of your cycle, we get the value of b sub 2 equal to 18.7 meters per second in 3 significant figures. So what is this speed? This is the instantaneous translational speed of the boulder when it reaches the boundary of the rough and the smooth surface. So it is a linear speed. All right. So we'll be using this in our succeeding uh, solution for determining the final translational speed of the boulder when it reaches the foot of the hill. From point 2 to point 3, the boulder is now sliding and not rolling, right? Because the lower half of the hill is covered with ice, so there is no friction, right? The boulder simply slides down from level 2 until it reaches the foot of the hill, right? So again, by the energy conservation law, right? Um, the translational kinetic energy acquired by the boulder at point 3, or we express that as 1 half times its mass, capital M, times b sub 3 squared, right? That's just equal to the mechanical energy of the boulder when it is exactly at level 2. That is 25.0 capital mg. That's the potential energy of the boulder at level 2. And 1 half times capital MB sub 2 squared. All right? This is the translational kinetic energy of the boulder, all right, at level 2, right? So from level 2 to level 3, take note, the boulder is simply sliding. It is not rolling anymore because the lower half of the hill is covered with ice. All right, so there is no friction. The boulder simply slides down until it reaches level 3 or the foot of the hill. That is why our conservation of mechanical energy equation is simply like this. All right. So when we cancel the mass capital M, okay, we can isolate the speed b sub 3 squared, right? That is, b sub 3 is our main target variable, right? So isolating b sub 3 squared, that makes it equal to 2 times, okay, there's a bracket, 25.0 g, right? Plus 0.5 quantity b sub 2 squared. Take note, we have to multiply 25 by acceleration due to gravity and then get the square of the value of b sub 2, which we earlier calculated as 18.7 meters per second. So when you square that and then multiply it by 0.5, okay, and then add it to the product of 25.0 g, and eventually multiply it by 2, okay, that is what we will be able to get, all right, for the value of b sub 3 squared. Moving on to our final computation for the speed b sub 3, all right, using this equation that we had earlier. B sub 3 squared equals 2 multiplied by 25.0 times g plus 0.5 multiplied by the square of b sub 2. So when we substitute the value for v sub 2, that is 18.7 meters per second, get its square, then multiply by 0.5, and then add to 25.0 g, then finally multiplying by 2 and getting the square root, all right? B sub 3 now will be equal to the square root of 2 times 245, right? This is the result of multiplying 25.0 by acceleration due to gravity, all right? 9.80 meters per second squared, that is. And then 175 is the result of multiplying the square of 18.7 meter per second by 0.5, that's 175. So finally, with the help of your scientific calculator, we can get the value of V3, which is 29.0 meters per second in three significant figures, right? So this is um, the translational speed of the boulder when it reaches the foot of the hill, which is the final answer to the question. So that's it, we're done. Till the next episode, mabuhay. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel.